The basic elements of electricity are very simple. If I can imagine point electrical charges in a vacuum, then there are positive charges and there are negative charges, and they attract each other or they repel each other with a force that varies inversely as the square of the distance between them. And that's really all there is to it. And yet it took thousands of years to figure that out, and even today, when we understand it very well, it's still confusing and difficult to learn about. Why is that true? Well, the reason it's true is because these elements of electricity, point charges in a vacuum, never exist in the real world. Electricity always exists in matter. And so in order to understand electricity, we must first understand matter. But matter is essentially electrical in nature. And so in order to understand matter, we must first understand electricity. And that's the crux of the dilemma that we want to speak about today.
At first glance, trying to see electricity in its true light seems as risky as a night out on the Las Vegas Strip. Electricity has numerous quantities: charge, potential, and field, to name a few. And with such a bewildering variety, it's hard to know which quantity to bet on. What's needed is a way to explain how everything fits together. A way to stack the deck in favor of good sense and clarity. What's needed is a surefire method behind this madness, the cause behind the effect of electricity. What's needed is a change of scene. On the surface, the electrical connection between Las Vegas and these Nevada hills isn't immediately obvious. For one thing, surveyors don't gamble. There's nothing random in the detailed precision of their maps, nor in their measurements that determine the height above sea level of each point on a predetermined grid. A line is drawn, connecting all points a certain height above sea level, and then repeated for other heights at regular intervals. To a practiced eye, the resulting contours of constant height give a clear representation of the real landscape. By the same token, the contours on this map give a clear representation of an electric field. These are contours of constant electric potential, and they too represent a terrain that has its ups and downs. When real ground goes up and down, the prudent traveler wants to know about it, because going uphill can be hard work. And exactly the same is true for electric potential. Moving up the incline of potential is hard work. And the steeper it is, the harder it is to climb. Of course, if the potential isn't changing, it takes no work at all. And if the potential decreases, the field is downhill all the way. In this analogy, electric potential is elevation, and electric field is the downward slope. To put it in more mathematical terms, the electric field is a negative derivative of the potential. Or, in other words, the potential is minus the integral of the electric field. The electric field of a single point charge is proportional to 1 over r squared. so its integral is proportional to 1 over r. For a single point charge, the direction of the field is pretty obvious. But what about more complicated situations? What does the electric field for this potential look like? Because it takes no work to move a charge along a curve of constant potential. There's no component of field in that direction. So the field is perpendicular to each equipotential at every point. And that's how it assumes its familiar shape. The familiar shape of even the most rugged terrain isn't all peaks and valleys. Some regions are perfectly flat and horizontal. A lake is a region of constant height above sea level. Just as a region of constant electric potential is created by a conductor in an electric field. And since electric potential is the same everywhere on the surface of a metal, the electric field is always perpendicular to that surface. Out in the hills, it's hard to find much that's perpendicular to anything. But in the city, it's easy. And here it's easy to find electricity at work and at play. Although this proliferation of light and color is probably not what the pioneers of electricity had in mind, they nevertheless laid the foundation for it. Ben Franklin did his part by bringing electric potential out of the heavens and down to earth. Thomas Edison, thinking more about work than play, captured electricity in glass and made it yield light. The eventual proliferation of neon signs was probably not even imagined by Georges Claude, the French physicist who developed a practical neon light in 1909. Those first neon lights were put to work in the Grand Palais in Paris, not as decoration, but as house lights. The reddish glow of those lights was seen as a drawback by everyone. Everyone but Jacques Fonseca, a publicist. In that red glow, he saw great possibilities. He persuaded Claude to sell him the rights, and by 1912, Paris had the world's first neon sign, and the work had barely begun. Electric potential is the ability to do work by making electric charges flow. And no matter where they go, their potential is measured in volts. But how big is a volt? And how many volts does it take to do a job? A flashlight